Okay, so in this section we're going to look at two types of quadrilaterals, neither of which are parallelograms. These are going to be called kites and trapezoids. Alright, so let's start by looking at a kite and what we can say about a kite. So what a kite is it's kind of like a rhombus, but it's longer on one side than the other. So two consecutive sides are going to be congruent, and then two other consecutive sides are going to be congruent. And there we have a kite. Okay, I'm going to label this kite A, B, C, D, and I'm actually going to build its two diagonals, and lo and behold, it looks like these diagonals are going to be perpendicular, and just like they are in a rhombus, and in fact they are. So we're going to actually take a minute, we're going to prove that. So we're going to say that I have this kite, and I'm going to say that AB is congruent to AD, and I'm going to say that BC is congruent to DC, so that's what I'm going to be given in this situation. And I want to prove that these two diagonals, BD and AC, are in fact perpendicular. Okay, so we're just diving right into the proof here. Alright, so right off the bat, I have all my givens. AB is congruent to AD. BC is congruent to DC, which is what's making this a kite. Okay, two sets of consecutive congruent sides. The next thing I can say here is that AC is congruent to itself. That's by the reflexive property, which now shows me that the top triangle and the bottom triangle are congruent. So triangle ABC has to be congruent to triangle ADC, and that's by SSS. Now, why did we do that? Well, we did that so that we could start talking about some angles here. So, if you take a look at things here, actually, we have to go a little bit further. We have to get, let's talk some angles here. Let's say that angle BCM has to be congruent to angle DCM. That's by CPCTC. Yep. And we can also say that MC is congruent to MC. That's by the reflexive property. Okay. So we just said that this angle is congruent to this one. This piece here, MC, is congruent to itself. It's going to give me side angle, side angle. So that's going to make these two triangles over here congruent. So triangle BCM has to be congruent to triangle DCM, and that is by side angle side. Now, let's hold this thought for a minute. I'm going to make some more room, and we'll keep going. So we just proved that the orange triangle there and the orange triangle in the bottom are in fact congruent. Okay, so we just said that these two orange triangles are congruent. This means that the measure, the measure of angle BMC has to equal the measure of angle DMC, because that's CPCTC, the corresponding parts are congruent, and that's two angles that correspond in those two triangles. Okay, so they're congruent. They're also adjacent, which means that the measure of angle BMC plus the measure of angle DMC has to equal to 180, because that's the angle addition postulate. Well, if I take out the DMC here and put in a BMC from here, that's going to give me 2 times the measure of angle BMC is equal to 180. I did that by substitution. divide both sides by 2. I get the measure of angle BMC is 90. That's the division property. And finally, if that is a 90-degree angle, this means in fact that BD is perpendicular to AC, because that is the definition of perpendicular lines. So we've just shown that if I have a kite, its diagonals have to be perpendicular. Okay, there's another thing that we can easily say about a kite, so let's get another kite up here and take a look at it. Okay, so let's build this same kite again. We're going to call this A, B, C, D. We're going to throw those diagonals back in, and we know these two are congruent, these two are congruent. So we're going to be given that AB is congruent to AD, and BC is congruent to DC. We want to prove. So this is what we're going to prove. We're going to prove that there's going to be at least one pair of congruent angles here. So we're going to prove that angle ABC is congruent to angle ADC. And this is like really straightforward. There's not a whole lot of work to this one. Because I have all this congruence here to begin with. AB is congruent to AD. BC is congruent to DC. That's given. That's just simply because it's a kite, right? AC again has to be congruent to itself. We used that in the last proof as well. That's reflexive, which gives me the top and the bottom triangles congruent. Triangle ABC has to be congruent to triangle ADC. We've seen this story before by SSS. And lo and behold, angle ABC and angle ADC are congruent parts of, or corresponding parts of these congruent triangles, so they are congruent. So that means that if I have a kite, these kind of outside angles, the one up top and the one on the bottom here, have to be themselves congruent. Alright, so that's all we're going to say about kites. Let's move on to trapezoids. Okay, so a trapezoid is very similar to a parallelogram, except for it only has one pair of congruent sides. And if we get lucky enough where, or sorry, it's not one pair of congruent sides, one pair of parallel sides. Sorry about that. If I get lucky enough where the non-parallel sides are in fact congruent, I get what's called an isosceles trapezoid, which is even better to work with. Alright, so we're going to call this isosceles trapezoid ABCD. And we are going to be given what we already know here. We know that AB is parallel to DC. And we know that AD is congruent to BC. What we're going to prove is that the base angles, so we're going to prove that angle D is congruent to angle C, so these two base angles are congruent. And likewise, we're also going to prove that angle DAB is congruent to angle CBA. Now, it seems like overkill to call these things anything other than angle A and angle B, but in a minute you're going to see that we're going to do some constructing here, so we're going to need these more robust names. So we're going to say that if this is an isosceles trapezoid, the two bottom angles are congruent, and so are the two top angles. Alright, so this takes some work to get through on this one. So let's get all of our givens out there. AB is parallel to DC. AD is congruent to BC. That is given, and that's making for us an isosceles trapezoid. Okay, so I'm going to construct two segments. We're going to drop down a segment here. We're going to call that point E. And we're going to drop down a segment there, and we're going to call that one point F. So we are constructing segment AE perpendicular to DC, and we're going to create also BF, which is also perpendicular to DC, And I can do this because through point not on a line, there exists a unique line perpendicular to the given line. So that's a lot, that's a bit of a mouthful, but if I have a line, DC, and I pick a point B that's perpendicular, or that's not on that line, there's only one perpendicular line that comes down, and that's going to be BF, likewise with AE. Okay, so that helps us out a bit, but because these lines are parallel, AB and what you call it, DC, that means that the two segments that I just created, segment AE and segment BF, have to be congruent, because the two lines have to be the same distance apart from each other if they are parallel. Alright, so I now have this is congruent to this. Okay, that's a right angle because that's a right angle. Lo and behold, I made two right triangles here. I have the hypotenuse and leg of each triangle. So the triangle AED has to be congruent to the triangle BFC, and that's because of HL. Alright, so just being clear on where we are with this. We now have this small triangle here and this triangle here being congruent, and we're going to leverage that to show that the base angles are also congruent. Okay, so we have these two congruent triangles here. Now let's kind of keep moving from there. We did that by HL. That means that angle C is in one of those and angle D is in the other. Those have to be congruent. That's by CPCTC. So that gets me one of the base angle pairs. Okay, and I have to do a little bit of other thinking here. Okay, and I have to use the fact that the top and the bottom are parallel here. I now also know that the measure of angle BAD plus the measure of angle D has to be equal to the measure of angle ABC plus the measure of angle C, and these both have to equal to 180 because these are same side interior angles. Okay, so and same side interior angles have to be supplementary. So these two pairings have to be equal, but now note this one has the C in it, that one has the D in it, and they're equal. So if I subtract the C from one side and the D from the other, I get the measure of angle BAD has to equal the measure of angle ABC by subtraction. Just subtracting angle D from one side and angle C from the other, and they're equal. So that's going to make that work. So I can just simply turn that into angle BAD is congruent to angle ABC, because that is the definition of congruent angles. All right. So what have we proven here? That if I have an isosceles trapezoid, then the base angles, whether they be the bottom ones or the top ones, in fact, must be congruent. All right. So we get a little bit more with the isosceles trapezoid. So let's try that. So let's build our isosceles trapezoid up here again. We're going to call this again A, B, C, D. These are parallel, these are congruent. And what we're going to focus in on is the two diagonals. And our argument here is going to be the given that AB is parallel to DC and AD is congruent to BC. Then we're going to be able to prove that the two diagonals, AC and DB, are in fact the same length, that they're congruent. Alright, so let's see if we can prove that. This is a matter of proving two triangles congruent. So if you're focusing in on this, the easy way to visualize this is we're going to prove there's one triangle here. I'll make it red. That one there. And I'm going to try to prove that. I'll make the other one blue, congruent to that triangle there. If I can prove that the red triangle is congruent to the blue triangle, then if you look carefully, the one diagonal is in the red triangle, the other diagonal is in the blue one, so we'll have it. Alright, so right off the bat, let's get the givens on the board. AB is parallel to DC. AD is congruent to BC. Both of those are given. Alright, so I also know that I can do something with an angle here. Angle ADC is in fact congruent to angle BCD because the base angles of an isosceles trapezoid are congruent. How do I know that? Because I just proved it moments ago. So those two angles, the ones in the bases, so this one in the red triangle and this one in the blue triangle have to be congruent. Alright, so finally I get that DC is congruent to itself. That's by the reflexive property, and that's in both the red and the blue triangle. So that tells me that triangle ADC is congruent to triangle BCD. That's going to be by side, angle, side. Side, the angle, and the side. The side, the angle, and the side of two triangles. And then I just get the two diagonals. Segment AC has to be congruent to segment BD by CPCTC. Oop, got the letters backwards there. Which, that's the proof that the diagonals of an isosceles trapezoid are in fact congruent. Okay, so one more trapezoid theorem and we are done for the day. So we're going to define something here. I'm going to say I have a trapezoid and I'm going to pick the midpoint of each side. So this is going to be, we'll call this point P, we'll call this one S, we'll call this one R, and we're going to call this one Q. Now I want to note that there is nothing about this that says it's an isosceles trapezoid. It just has to be a trapezoid. Okay, and I'm going to pick the midpoint here, and I'll pick the midpoint over here. I'm going to call that M, we're going to call that N, and if I connect those two midpoints, that segment is called a mid segment. So this is the mid segment of the trapezoid. And our assertion here is that it's two things. So one, MN is going to be parallel to QR and parallel to PS. And two, the length of MN is equal to the length of QR plus the length of PS divided by 2. That's a little bit more convoluted, but I'm arguing that if I take the average of the top and the bottom, I get the length of the middle. Alright, so the best way to kind of go forward on this is to actually place this thing in the coordinate plane. So I'm going to put P at the point 0, 0, and I'm going to carefully locate the other vertices. We're going to put S here at the point C plus 2D 0. Okay, but that's going to have R at CB. Or sorry, not B, but 2B. Okay, so what's going on here is that R is above this. I'm at C there. I'm going to go a little bit further over, 2D over, and back to 0 gets me to there. And Q is going to be located at 2A, comma 2B. Okay, so my argument is that if I carefully locate these points, I should be able to prove these things. So using midpoints, M has to be, well, half of 2A is A, half of 2b is b, which is m at the point AB. N has to be, well, let's see, halfway between C and C plus 2D. Well, let's see. That's going to give me 2C plus 2D. So N is going to be at C plus D. And halfway between 2B and 0 is B. Now note, these are not changing in the y direction. So the slope of Mn has to be 0 over something, which makes it 0. So its slope is 0. Note, neither the bases are either changing in the y direction, so all of their slopes have to be 0. So if the slope of all of them is 0, then we know that Mn is parallel to QR, is parallel to PS, because they all have the same slope. Finally, we want to work out that Mn is half the size, or the average of the other two. Well, let's look at the length of Mn. Mn is just going from A to C plus D, so the length of Mn has to be C plus D minus A. Let's see, the length of QR has to be, let's see, we're going from 2A to C, so that has to be C minus 2A. The length of PS, we're going from 0 to C plus 2D, so that has to be C plus 2D. So if I take QR plus PS, I'm going to get 2C plus 2D minus 2A. And if I divide that all by 2, the 2's all cancel, leaving me with C plus D minus A. So that gives me that Mn has to be half the sum of the other two sides. So the mid segment has to be the average of these two lengths, and it has to be parallel to the other two. Alright, so let's summarize here. For kites, right, so kites are like this. We know that the diagonals are perpendicular, that's 1. And we're also given that these two angles have to be congruent. For trapezoids, when they are isosceles, right, we get the base angles are congruent, and we also get that the two diagonals have to be congruent. Right, and if I have any old trapezoid, right, so it doesn't have to be isosceles. If I join the mid segments, this all has to be parallel, and if this is A, B, and C, then B has to equal A plus C over 2. Alright, so there's kind of a summary of what we did today.